Dear students, let's continue with solution chapter. Till now, in this chapter, we have already discussed different ways to express the concentration of solution. That is molarity, mole fraction, ppm, mass percentage and volume percentage. We have also discussed Henry's law, which is about the solubility of gases in liquids, which states that the partial pressure of a gas over the surface of liquid is directly proportional to the solubility of that gas in the liquid. We have also discussed Raoult's law, which states that for a solution containing two volatile components, partial pressure of each component is directly proportional to the mole fraction of that component in the solution. Then we have discussed that Raoult's law is a special case of Henry's law. Then graphical representation of Raoult's law. Today's topic is classification of solutions. As we have two types of people, ideal and non-ideal. Similarly, solutions are also classified into ideal solution and non-ideal solution. What are ideal solutions? The solutions which obey Raoult's law over the entire range of concentration. So one of the condition of ideal solution is that which obey Raoult's law at all concentrations. What does it mean? Raoult's law says that partial pressure of a component is directly proportional to its mole fraction. So if you remember, according to the graphical representation, if you take mole fraction on x-axis and vapor pressure on the y-axis, then the graph somehow comes to be like this, which indicates that if you increase the mole fraction, from, maybe it is a component, from XA0 to XA1, then if you increase the mole fraction, vapor pressure keeps on increasing. And if I talk about B component, then if you decrease the B component from 1 to 0, it becomes something of this sort. If we decrease the mole fraction, that means the solubility of that particular component in the solution, then it keeps on decreasing, and this is the overall. So if the graph is something like this, we already know that partial pressure of a component is directly proportional to its mole fraction. If mole fraction of a component increases, partial pressure also increases. The same is indicated here. If it changes from 0 to 1, then partial vapor pressure also increases. Similarly, for B, we can say partial pressure of B is directly proportional to its mole fraction. Here, mole fraction changes from 1 to 0. So, the same way, this is the indication for that it keeps on decreasing with the decrease in mole fraction. So, this is for B component and this is for A component. So, if a solution obeys Raoult's law, means mole fraction increases, then partial vapor pressure also increases, then we say it is an ideal solution. This is one of the conditions. What is the second condition? Second condition says that delta V mixing is equal to 0. What does it mean? If you take two, naturally we are taking two components in the solution. It is a binary solution. If I take 5 ml of A component and 5 ml of B component, after mixing, if it comes out to be 5 plus 5, which is equal to 10, then it is an ideal solution. You will doubt 5 plus 5 is always 10, but you will come to know after a few minutes that it doesn't happen in all the cases. So in ideal solution, if you mix the two components of a particular volume, then their sum total will be equal to the volumes of the volume of each component. So if I take 5 ml of one component, 5 ml of B component, it comes out to be 10. Means even after mixing the two components, there is no change in the volume. Before mixing and after mixing, volumes remains the same. Third point is delta H mixing is also equal to 0. What does it mean? That neither delta H is what? Enthalpy change. Enthalpy change before mixing and after mixing, that remains the same. Neither heat is absorbed nor heat is evolved. It means neither the reaction is endothermic nor the reaction is exothermic. There is no change in the enthalpy of reaction. So it is exactly equal to 0. Such solutions are called as ideal solution. What happens in all such cases? Like what is the reason behind? Let me talk about it. So here fourth point is there, which I'll explain. Why does it happen? Why some of the solution they behave ideally? Let's talk about it. I'll take the case of hexane and heptane. Hexane plus heptane, which is an example of ideal solution. Or these are the examples. Or the another example is, I may say chloroethane and bromoethane. I'll start with this example. You'll understand the concept. When hexane and heptane are mixed together, they get mixed in such a way as if they have been mixed with their own component. So shall I say, whatever is the force of attraction, intermolecular forces of attraction between hexane and hexane, between heptane and heptane, the same kind of intermolecular attractive forces are present between hexane and heptane. So I'll say this is A component and this one is B component. Sorry, I'll write it here. This is A component and this is B component. So what is the reason? Why do they behave ideally? Because AA forces of attraction and BB forces of attraction are equal to AB force of attraction. What does it mean? It means whatever is the force of attraction between solvent and solvent, solute and solute, they are of the same nature, of the same strength as the force of attraction present between A and B. That is why when solvent and solute are mixed together, when hexane and heptane are mixed together, when chloroethane and bromoethane are mixed together, they behave as if they have been mixed with the another liquid of their own kind. So that is why there is no change in the enthalpy, there is no change in the volume, and they behave as ideal solution. They obey Raoult's law at all the concentration, at all the mole fractions. Such solutions which follow these three conditions, that is, they obey Raoult's law. Delta V mixing means there is no change in their volume even after the mixing. There is no change in their enthalpy, neither heat is absorbed or evolved after mixing of the solution. They are called as ideal solutions. I think you are clear about ideal solutions. Let's talk about non-ideal solution. Non-ideal solutions are of two types. One which shows positive deviation from Raoult's law, and another is the solutions which show negative deviation from Raoult's law. What does it mean? Positive deviation from Raoult's law. Their graph is not a straight line graph. If I plot mole fraction here and vapor pressure here, you will see the graph is supposed to be like this, but it doesn't come out to be this. Somehow this is showing this kind of graph. Another solution, you are supposed to be something like this, but it comes out to be like this. And when you join the two, we are expecting this kind of graph, but it comes out to be like this. There is change, so it is not behaving ideally. Why? Because there is no straight line at all the concentration. Here it is behaving, here also it is behaving according to the Raoult's law, but here there is a change, there is no straight line. I mean, it's a kind of parabola. Why is it so? I'll explain it, but just see the condition. So one is they do not obey Raoult's law. They show positive deviation from Raoult's law. Another is, I'll say, where delta V mixing is greater than 0. What does it mean? It is positive. Greater than 0 means it is positive. So what does it indicates that if I take 5 ml of a component, 5 ml of another component, it is not coming out to be equal to 10. Rather, it may be somewhat greater than 10. It could be 10.1, it could be 10.2, somewhat greater. When the two components are mixed together, there is increase in their volume. So whenever there is positive deviation, delta V mixing is coming out to be positive. Third condition is delta H mixing is also greater than 0 because it is positive deviation. So delta H mixing is also positive. Positive means when delta H is positive. Positive means it is endothermic reaction. You have already done in junior classes. It is an endothermic reaction. What happens in endothermic reaction? They are carried out with absorption of heat. So when the two components are mixed together and absorption of heat of the system takes place, then solution becomes cold. So if a question comes, the two components are mixed together and finally the solution which is obtained is slightly colder. What kind of deviation it shows from Raoult's law? You will say it shows positive deviation from Raoult's law. So, but why is it happening? You know, what is the reason behind it? Why does it happen so? I'll explain it with the help of an example. And the example here is ethanol and acetone. You know, in pure ethanol, there is strong intermolecular attractive forces, which is hydrogen bond. So if I say this is C2H5OH and this is another molecule of C2H5OH, then there is strong hydrogen bond between the hydrogen of ethanol and oxygen of another molecule of ethanol. When acetone is added to this, acetone is CH3COCH3. It occupies the space in between the two molecules of ethanol, and due to this, weakening of intermolecular forces of attraction takes place. So shall I say AA interactions means solvent-solvent interaction, which is between ethanol and ethanol, and BB interaction, AA and BB interactions in this case are greater than AB interaction. Final force of attraction between acetone and ethanol is not as strong as in the case of AA and BB. So solvent-solvent and solute-solute interactions are stronger than solvent-solute interaction. Solvent-solute interactions are weaker. When they are weaker, they can evaporate faster. Their escaping tendency increases, and when it increases, vapor pressure increases at the same mole fraction. At this mole fraction, the expected vapor pressure is this one. but it comes out to be, expected vapor pressure is this, but at the same mole fraction, vapor pressure comes out to be this. So there is increase in the vapor pressure. Expected is this one, and at this mole fraction, expected vapor pressure is this, but it is coming out to be this due to this parabolic graph. So there is increase in vapor pressure at the same mole fraction. Why does it happen so? Because intermolecular forces of attraction in solvent and solute is weaker than the solvent and solute. When forces of attraction are weaker, escaping tendency increases, vapor pressure increases. So at the same mole fraction, they show higher vapor pressure than the expected one. So they show positive deviation. That is why the final forces of attraction are weaker. So there is increase in the volume after mixing, and there is enthalpy change is also positive. This kind of reaction is carried out by absorption of heat. So this is about non-ideal solution showing positive deviation from Raoult's law. Other example of this type could be acetone, benzene, or it may be acetone or carbon disulfide. You may learn at least one example of each type. Let's talk about negative deviation from Raoult's law. Exactly on the same way, I will say they also don't obey. They show negative. One is they show negative deviation from Raoult's law. Second is delta V mixing. Here in this case is less than 0. It means if I take 5 ml of one component, 5 ml of another one, it is also not equal to 10, but it may be equal to maybe 9.9 or 9.8 or 9.5, something like this, but less than 10. And if I find out delta H mixing, it also comes out to be less than 0. It means it is negative. Whenever delta H mixing is negative, it means it is an exothermic solution. Exothermic solutions are carried out with the evolution of heat. So it is exothermic reaction. When the two components are mixed together, heat is evolved. And when heat is evolved in the beaker, it becomes hot solution. It is a warm solution which is formed. And I'll explain it with the help of the graph. I'm saying it shows negative deviation from Raoult's law. Again, I'm plotting mole fraction here, vapor pressure here. Expected graph is something like this, but it comes out to be this way. Similarly, another graph is this, but it also comes out to be like this. Overall graph should be like this, but it is also like this. So at this mole fraction, vapor pressure should be this much, but it is not to this extent, rather it is here only. So there is decrease in the vapor pressure. So it shows negative deviation from Raoult's law. But why is it happening so? Again, I'll explain it with the help of an example. Chloroform and acetone. You know, initially there are not very strong forces of attraction between chloroform and chloroform, as well as in acetone and acetone. But when the two joins together, they are bonded with hydrogen bond like this. This is chloroform. This is acetone. Hydrogen of chloroform and oxygen of acetone makes intermolecular hydrogen bond. So in this case, I can say AA interaction and BB interactions like chloroform and acetone are weaker than AB interaction. So let me summarize it again. Solvent interaction, solute interaction are weaker than the solvent-solute interaction. After mixing, forces of attraction have come into picture, which are stronger. So after the formation of solution, strong forces of attraction are formed, they are joined together by hydrogen bond, escaping tendency decreases. When they are not able to evaporate, vapor pressure decreases relatively. So that is why there is a decrease in the vapor pressure here. And that is why volume, because they are joined with each other with the strong forces, so volume also decreases, and such reactions are carried out with the absorption of heat. Other example of this type are chloroform and diethyl ether, and it could be chloroform and benzene. Children, let me revise what we have done till now. Till now we have done, there are two types of solution. One is ideal solution, other is non-ideal. Ideal, which obeys Raoult's law at all concentration. Delta H mixing is 0, delta V mixing is 0, and why? Because AA interactions and BB interactions are equal to AB interaction. And then we have done non-ideal solution, which shows positive deviation as well as negative deviation. Why does it happen so? Positive, because the final forces of attraction which are formed between solvent and solute are less than the solvent-solvent and solute-solute forces of attraction. And in case of negative deviation, it is the opposite. That is, solvent-solvent and solute-solute interaction is actually less than the solvent-solute interaction. So finally, forces of attraction are greater. So escaping tendency decreases and vapor pressure also decreases. Children, azeotropes are the binary mixtures which have same composition in liquid and vapor phase. They are constant boiling mixtures. What does it mean? Like you have water, it has a particular specific boiling point. When I mix some another component, its boiling point is naturally different from water. But you will be surprised to know that when the two components are mixed together, they will boil at another boiling temperature which is different from water and that particular component. They boil at the same temperature. How is it possible? So let me talk about azeotropes. So you may write down, it is defined as the binary solution which have same composition in liquid as well as vapor phase. They are also called as constant boiling mixtures at a particular composition, at definite composition. So I'll explain it further with the help of two examples. Azeotropes are classified into two. One is minimum boiling azeotrope, and another is maximum boiling azeotrope. Children, in order to explain minimum boiling azeotrope, I'll take the example of 72% propanol, which is C3H7OH. What does it mean? It means 72 ml propanol, which is mixed with 28 ml of water. See how it acts as minimum boiling azeotrope. You already know that the boiling temperature of water is 100 degrees Celsius and of propanol is 97 degrees Celsius, and the mixture of two, which is, this is C3H7OH plus water, in which ratio? 72% of propanol. It's surprisingly, its boiling point comes out to be 77 degrees Celsius, which is much lower than the boiling point of water as well as of C3H7OH. So its two components have boiling point 197, but this mixture its boiling point is much lower than the independent components. So can we say it is minimum boiling azeotrope? It boils both the component, they boil at the same temperature, although their individual boiling points are different, and it is much below than 100 and 97. So it is called as minimum boiling azeotrope. Which solutions will act as minimum boiling azeotrope? All those solutions which show positive deviation from Raoult's law. Positive deviation from Raoult's law will show this. How is it possible? Who shows positive deviation from the Raoult's law? Which has more vapor pressure than the usual one. Whereas this is about the boiling point. This is about vapor pressure. For the time being, you may learn that boiling point is inversely proportional to vapor pressure. Maybe in the next class I'll explain why the relation is of inverse between the two. So if the boiling point increases, vapor pressure decreases. So if any solution shows positive deviation from Raoult's law, it will definitely have lesser boiling point, so they'll come under minimum boiling azeotrope. I'll take one more example of it. You know, ethanol, it is generally mixed with water, and in order to obtain pure ethanol, we do fractional distillation. And when you do fractional distillation, it keeps on, it gets separated from water, and a stage will come when it becomes 95% ethanol. This is called as rectified spirit. It is different from medical spirit. Just find out the difference between rectified spirit and your medical spirit. Once it attains this composition in which 95% ethanol is there and 5 ml water is there, then if you want to further purify it, if you want to further remove 5 ml water out of it, it is very difficult. It cannot be done by fractional distillation. Why? So the question is asked generally in the board examination, why you cannot separate water from 95% ethanol? Why you cannot obtain pure ethanol, which is 100% ethanol, which is called as absolute alcohol, from this by fractional distillation? Because now it has become an azeotrope, and once it is azeotrope, both water under this composition, 95% ethanol, both water and ethanol will boil at the same temperature. Whatever is the composition in the liquid phase, the same composition will be there in the vapor phase. So you cannot separate ethanol and water at this stage once it has attained the azeotropic composition. So this is very surprising. Then how will you separate? Although it is not mentioned in the NCERT, but in the entrance examination sometimes it is asked. So you can separate it by azeotropic distillation. What is that? Just mix it with the benzene, and then you get 3 fractions, and in the last fraction, you'll get absolute alcohol. So I think you are clear with minimum boiling azeotrope. Let's move on to maximum boiling azeotrope. I'll take an example in order to explain maximum boiling azeotrope, and it is 68% HNO3. What does it mean? It means it is equal to 68 ml of nitric acid plus 32 ml of water. Let's see what are their boiling temperatures. So I'll write down the boiling temperature here. For water, the boiling point is 100 degrees Celsius, whereas for HNO3, boiling point is 86 degrees Celsius, and for this azeotropic mixture, which is HNO3 plus water, and the composition is also fixed, which is 68%, the boiling point, again it is very surprising, it is 122.5 degrees Celsius. Boiling point is much higher than the individual components of the mixture. One is 100, other is 86, and now it is 122. Now both of them, even water is boiling at this high temperature. Both of them, they behave as a pure component, pure liquid. And they are also called as, all azeotropes are called as constant boiling mixtures, because they are boiling at the constant temperature irrespective of their nature at a definite composition. So why I am saying this is maximum boiling azeotrope, because the boiling point of this mixture at this composition is much higher than the boiling point of these two. And naturally, who will show this kind of, who will make this kind of azeotrope? One which shows negative deviation from, so you can learn all those solutions which show negative deviation from Raoult's law will show this kind of azeotrope. Children, so now we are coming to the end of this class. Let me revise again, summarize the things. One, we have done ideal and non-ideal solution. Ideal, which obeys Raoult's law, where the delta H mixing is 0, delta V mixing is also 0. Whereas in non-ideal solution, they are of two types, which shows positive deviation and negative deviation. Positive deviation is, the reason behind is where the intermolecular forces of attraction between solvent and solute is less than the solvent-solvent and solute-solute interaction, whereas in negative deviation, final forces of attraction, that is between solvent and solute, is much higher than the solvent-solvent and solute-solute. So escaping tendency decreases and it shows negative deviation. Then we have also discussed azeotropes. Azeotropes are constant boiling mixtures at a definite composition. Their boiling point is constant. Their composition remains same in liquid as well as in vapor phase. They are binary mixtures, of course. They are of two types, minimum boiling azeotrope and maximum boiling azeotrope. Just learn that if the boiling point is minimum, that will be shown by those solutions which show positive deviation, because we have done boiling point is inversely proportional to vapor pressure, whereas in maximum boiling azeotrope, they will be shown by those which show negative deviation from the Raoult's law. Azeotropes are of two types, minimum boiling azeotrope and maximum boiling azeotrope. Minimum boiling azeotropes are those which boil at much lower temperature than their individual components, and it will be shown by those solutions which show positive deviation from the Raoult's law. Whereas the another one, which is maximum boiling azeotrope, these solutions will boil at much higher temperature than the individual components, and of course this will be shown by those solutions which show negative deviation from Raoult's law. So children, hoping to see you again in the next class, and till then, goodbye.